In this video, you will learn how to simplify a trigonometric expression. The first thing you'll notice are our reciprocal identities. These are identities that you should already be familiar with. Basically, if I wanted to know what sine was as another function, I could take its reciprocal and do 1 divided by that other function. Likewise, cosine and secant are reciprocals, as are tangent and cotangent. Some new identities that we have talked briefly about last chapter are our quotient identities. These are very useful when you're trying to get everything in terms of just sine or just cosine. So whenever you have tangent and you need it to get to be either a sine or a cosine or cotangent, you're most likely going to replace it with one of these quotient identities. Another identity that was very useful are some called the Pythagorean identities. There are actually 9 of these in total, but really 3 are what you're going to want to remember. Now these come from our Pythagorean theorem, which you'll recall is a squared, a leg, plus b squared, another leg, and that equals the hypotenuse squared of a right triangle. Well, from our unit circle, we have a leg, which is the x value, a second leg, the y value, and it happens that cosine is that x value, sine is that y value. So with our Pythagorean theorem, I could take cosine squared and add to that sine squared and get our radius squared, which 1 squared is just 1. Anytime you have cosine squared plus sine squared, that means you can replace those two terms with a value of 1. Now we also have 2 more Pythagorean identities. The first one we'll get by dividing sine squared and cosine squared by the value of sine squared. You know that anything divided by itself is a value of 1. If we look at our quotient identities, cosine divided by sine is cotangent. Even though we're dividing cosine squared by sine squared, we can still use the quotient identity. It will just give us cotangent squared. Then if we look to the reciprocal identities, 1 divided by sine is cosecant. And so again, because this is 1 divided by sine squared, it will give us cosecant squared. Likewise, if we look at the same Pythagorean identity, sine squared plus cosine squared equal to 1, and divide everything by cosine squared, again, with our quotients, sine divided by cosine is tangent. Because these are squared, they will give us tangent squared. Anything divided by itself is 1. And again, for our reciprocal identities, 1 divided by cosine is secant. And so we will get secant squared if we did 1 over cosine squared. These are 2 other Pythagorean identities which are very useful. From each of these 3 identities, you can actually get 2 more by manipulating the equation, essentially moving 1 terms from one side of the equation to the other. So let's take cosine squared plus sine squared equal to 1. If I were to subtract sine squared from each side, it would give me another Pythagorean identity of cosine squared equals 1 minus sine squared. Likewise, if you were to take the same identity, but this time subtract cosine squared from each side, you will get sine squared equal to 1 minus cosine squared. you can follow the same idea for each of the other two. So let's write each of our other Pythagorean identities in. Again, we just found the other two for the first identity. For our second identity, if we subtracted cotangent squared to the other side, we would have 1 equals cosecant squared minus cotangent squared. If we had subtracted 1 to the other side, you would have cotangent squared equals cosecant squared minus 1. On our third identity, if we again first subtract the tangent squared to the other side, I will have 1 equals secant squared minus tangent squared. And if I subtract 1 to the other side, I am left with tangent squared equals secant squared minus 1. Each of these Pythagorean identities can be used at any point if you have two terms that are the identity, and you can replace those two terms with the one it's equal to. Rarely, you might also replace one term with two, depending on the situation. Let's now look at our last two sets of identities. Here you'll notice some identities we call cofunction identities. All of these identities will have pi over 2 minus x, and then if you notice, it equals a different function. The last set are what we call negative angle identities. If you were to take the sine or cosecant, tangent or cotangent of a negative angle measure, it would give you a negative function. Cosine and its reciprocal secant, though, if you took a negative angle of that, you would still have a positive function. All of these identities you will need to know how to use. You will be given a formula sheet with the unit circle for this entire chapter, and therefore you do not have to memorize any of the identities, but you need to be familiar with them enough that you can use them quickly. Something else I would like to show you are some steps as far as the order in which you would want to try to do different things to simplify a trigonometric expression. There are of course many ways to simplify an expression. I have found that for most of the time, if you follow these steps and try these things first, it will be easier. So the first thing I would try is to get rid of any cofunction or negative angles. Replace what you see as the cofunction with the function it is equal to. Next, I would try getting rid of any Pythagorean identities. Again, this means if you have two terms of the Pythagorean identity, replace it with the one term it is equal to. Next, if you have fractions, you're going to want to try to get it so there's just one fraction or one term, and that would require you to make common denominators. Another thing you can do is try to factor. By factor, I would mean taking out a GCF, or it could also mean factoring something that was quadratic to degree 2. Your last option is to make sure that every single function is either a sine function or a cosine function. Again, that would be predominantly using our quotient identities to make tangent sine and cosine, or cotangent sine and cosine. Let's now look at an example on the next page. In this example, we wanted to simplify this trigonometric expression. So again, the first step is to look for any cofunction identities. Here, tangent of pi over 2 minus theta, theta again being a variable such as x, you can replace it with what it's equivalent to. Next, I want to look for any Pythagorean identities. We do not have any identities here. There's only one term. I do not have any fractions. I have no GCF to factor out. And so now I want to put everything in terms of sine or cosine functions. Sine is already that function. But cotangent, I can replace using the quotient identity with cosine divided by sine. That would then allow me to have cosine times sine and sine times 1. And since one sine is in the numerator and 1 is in the denominator, those cancel out, leave me with just a cosine function. You can assume that you are fully simplified when you have just one function or one term. You will not always be able to get it this simplified, but that is your goal. Let's now try to do some together. In this first problem here, again, I'm looking for cofunction and negative angles. I do not have either. Next, I want to look for a Pythagorean identity. I don't see one of our Pythagorean identities exactly, plus both terms are not squared, so I can rule that out. I don't have fractions, but I do have a cosine function in the first term and a cosine function in the second term. And so that will allow me to factor out a GCF of cosine. Remember, to factor a GCF out, you want to take the original terms. And since factoring is the operation of division, we're going to divide each term by our GCF. When I do that, I have cosine divided by cosine, and anything divided by itself is a value of 1. Same thing happens in the other term, but I was left with a sine squared. Next, I want to again start at the top of my steps. I do not have any cofunction or negative angles, but now I do notice that I have a Pythagorean identity. 1 minus sine squared is the manipulation of the original cosine squared plus sine squared equals to 1. This is the same thing as if I had cosine squared. So I can replace all of that Pythagorean identity and get just the one term cosine squared. Once I've done the Pythagorean identity, you want to try to simplify every time before going back to the top of your steps. Well, cosine to the first power times cosine squared would give me cosine to the third power. Because when I multiply with the same base, I want to add the exponents. Since that is just one term, I know that I'm done. Why don't you please pause the video and do example 2. There are two ways to do example 2. One option that is the fastest does not actually follow the steps. Some of you might have realized that sine divided by cosine is the same thing as tangent. And again, because both the sine and the cosine functions are squared, that would be the same thing as tangent squared. Once I've done that, this is now one of our Pythagorean identities. This is the Pythagorean identity we got when we divided the original identity by cosine squared. It's just the 1 and the tangent square switched places. So I can replace all of that Pythagorean identity with secant squared. Again, I have one function, so I know I'm done. It's not always easy to see something like that. So again, there's more than one way to do this. If you had followed my order of steps, you probably would have tried to get a common denominator for your two terms to make it one fraction. Since our denominator is cosine, if I were to take cosine as a denominator and want to have a value of 1, I would need to have cosine squared in the numerator as well. Now that I have a common denominator, I can go ahead and add the numerators. When I do that, I notice that again I have a Pythagorean identity. Cosine squared plus sine squared is 1. And 1 over cosine squared is another reciprocal identity, which gives me the secant squared we got by doing the first method. Let's move on to number 3. What you should notice that in number 3 is you have a cofunction identity. Again, replacing cofunction identities and negative angles should be one of the first things you do. The sine of pi over 2 minus theta is the same thing as the cosine of theta. Why don't you try to finish this from here, pause the video, and come back when you're done. From here, I notice that I have a cosine and then I have cotangent. As far as my steps, there's no Pythagorean identity, and I don't have to get common denominators to add these fractions because I'm not adding them, I'm multiplying. There's nothing in common to factor, so I want to put things in terms of sine and cosine. Putting things in terms of sine and cosine is always a good go-to if you're not sure what else to do. So cotangent, if I look at my quotient identities, is the same thing as cosine over sine. If I were to now look at these and multiply, I see that I have a cosine in both the numerator and the denominator, and so they cancel out, leaving me with 1 over sine. Now, this is one term, but it is not proper to leave something that you can still simplify. So since this is a fraction, and I could use a reciprocal identity to make it just cosecant, that's what we want to do. Let's move on to number 4. In number 4, again, I'm going to notice right away that I have a negative angle function. Now, this one is special because this one isn't just a negative angle. This is cosine squared of a negative angle. And what that means, if I square something, I'm multiplying the cosine of negative x times the cosine of negative x. If I simplify both of those negative angle identities separately, cosine of a negative angle happens to be another positive function. And so I'm still going to get cosine times cosine, which is just cosine squared. And again, positive cosine squared. But be careful because that only happens for cosine and secant. Had that been sine squared of negative x, some people will mistakenly give me negative sine squared of x. But that would not be the case because the negative times the negative would have given me a positive. So now that we have simplified that negative angle identity, I'm again at a spot where I can't do Pythagorean identity. I already have one fraction and there's nothing to factor out. I want to put things in terms of sine and cosine. And so again, that quotient identity for cotangent says that cotangent squared is the same thing as cosine squared over sine squared. From here, we have to remember how to get rid of a fraction within a fraction. We want to multiply by the reciprocal of the denominator. When I do that in the denominator, it completely cancels out. That's the point. But you also have to multiply the numerator by the reciprocal. Here, that's going to cancel out our cosines, leaving me with just the sine squared x. Please now pause the video and complete number 5. When I look at number 5, I see right away that I have a Pythagorean identity. So that's one of the first things I want to change. I'm going to replace 1 plus cotangent squared x with its Pythagorean identity of what it's equal to, cosecant squared x. This basically means I have something like an x divided by an x squared. You know that when you're dividing with the same base, you subtract the exponents. And so this is the same thing as having cosecant to the negative 1, but we also know that we don't ever leave negative exponents, and so we'll put that in the denominator. Lastly, if I look at this, this is not as simple as I could be. I could do the reciprocal function to get an answer of sine. Please now do number 6 and pause the video. Please now pause the video and do number 6. For number 6, here I just want to right away put things in terms of sine and cosine. If I do that, I have a fraction within a fraction again. So I want to multiply both the denominator and the numerator by the reciprocal of my denominator. Again, doing that gets rid of your original denominator completely, which is the point. And here, cosine times cosine is going to be cosine squared. One term, so that is my final answer. Please now complete your worksheet, which is homework.